Okay, all right, let's get going. Today's lesson will be a lot like last time's lesson. Make sure you got your notepads ready. We're going to watch a video. You're going to take some notes on it. I'm going to throw you into some breakout rooms. We're going to take some notes. We're going to watch the third motion, or third law of motion. And then we're going to do an in-class, okay, so what does this mean? Kind of quiz, but not for a grade. Okay? And that's all we're doing today. Oh, nope, stop. There we go. The second law first. All right, you got your notes ready? You ready to go? Could you hear when the sound went? Just you always need to double check because the technical issues abound everywhere.
To be an NFL kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics.
It's easy to say, well, I just kicked the ball. Well, let's delve into it. Let's look at the specifics. What actually happens when you kick the ball, and why does the ball go where you ask it to go? And it is Newton's second law of motion.
The second law is one of three laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move.
So the second law says if you have an object with a mass that is accelerating, and acceleration means a change in velocity, that is equal to the amount of force applied to the object. The way we say it with words is F is equal to ma.
This also means that in order for an object like a football to accelerate, a force must be applied. To illustrate Newton's second law in kicking, we asked Morton Anderson, the NFL's all-time scoring leader, to perform his craft in front of a high-speed phantom camera. The entire procedure unfolds in less than a second and a half, from snap to hold to kick.
It's all about training and rehearsing and doing something over and over and over again.
To reduce the chance of a block, NFL kickers take just 3 steps to the ball. The final step is with the plant foot, which provides the stable platform for the kick.
I call it the moment of truth. And the moment of truth is basically when your plant foot hits the ground next to the ball. You're either in the right position or the wrong position.
The kick itself involves the entire leg building the force necessary to launch the football.
It's a hammer, and you're swinging the hammer, and you're trusting it, and it's going to be, it's going to be impacting the ball with great velocity.
An NFL kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. This quick, violent strike is a perfect example of what's known in physics as an impulse.
Impulse is an important concept because there is a finite time over which the foot is in contact with the ball, and during that time there's a force applied to the football.
An impulse is equal to the force multiplied by the time the force is applied, represented by delta T. If force is graphed versus time, it's possible to see how a larger force or a longer time for the force supplies a bigger impulse.
Since impulse is really just the change in momentum, and since the ball doesn't change its mass, we're really just talking about the change in the speed. The bigger the impulse, the bigger the change in speed, which means the faster the ball is moving after it leaves the kicker's foot.
Ironically, Anderson says the distance of the field goal doesn't change his approach to the kick itself.
Mentally, you want to look at a 50-plus yarder, like a 40-some yarder, with some room to spare. I think that's a good way to kind of fool yourself into thinking it's a shorter kick.
Whether the kick is short or long, Newton's second law explains what an NFL kicker must do to send a football through the uprights.
All right, Cade, you're the first one on my screen. Go ahead and share something with us.
Nothing can move if a force is not applied to it.
Perfect. Philip, you're next.
Impulse is force times time multiplied by time.
Impulse, force times time. Now, I will admit that equation we're going to not be using much right now, but it most definitely will come up later. And keep that equation in mind because we're going to do a unit on car safety features. That equation right there dictates almost every car safety feature. Okay?
Now that I've gone, do you mind if I go to the bathroom real quick?
I want you to have this full list.
Okay.
So you can,
Thank you.
but just
I
don't
can
keep
wait.
scrolling. Okay. Tanner.
An impulse is the change in speed.
Impulse, it looks at the change in speed. Or rather, let's say it this way, it describes the change in speed. So just to say the word is, the only reason I'm changing your wording is mathematically. I can't remember if I brought it up in this class or not. Just a little side note here. The word is an equal sign in math. And so if we say that impulse is speed or a change in speed, then we're quite literally saying that it has the same units as velocity and it's got different units. So since they're not equal to each other, then I'm pulling out that word, simple word. But mathematically, I'm bringing this up because this is a hint to you on word problems. Anytime you see the word is or any verb, that's where your equal sign goes in the equation. It's really helpful to a little helpful fact for word problems. So I'm very glad you brought it up that way because that's a lot of people haven't taught others how to read a word problem. Gage, you still with us? But anytime you see the word is or any other verb, could be ran, whatever, that is going to be the location of your equal sign when you make an equation out of the sentence. Super helpful. All right. Gage, you're next.
When kicking a football in the NFL, Newton's second law is required.
There we go. When kicking a football, and I would even venture to say, even if you kick a football but you're not in the NFL, Newton's second law applies. Do you agree with that? And I would even say it's required because of that first thing that was put on the screen. The whole idea is you want it to move. All right. Now, Philip, I will say at this point, I've scrolled my screen. If you need to use the bathroom really quick, I bet you can be back by the time that we get to the bottom of the screen and you'll have time to take a screenshot and write these things down.
We had ghost pepper chili last night. It won't be real quick.
Well, yeah, in that case, wait as long as you can. Emily.
I said that the bigger the impulse, the bigger the change.
Do you remember the change in what?
Speed.
Uh-huh. The bigger the impulse, the bigger the change. Typically in speed is what we're looking at. It also can be a change in force, but we almost every problem we're going to do, we're going to be looking at a change in speed. How did you change your speed? You were going from 0 to 60. Did you do that over 5 seconds, 10 seconds? Did you do that over a minute and a half? Because how you change your speed, even though we have the same start and same finish, that of course would affect the force our bodies feel in that process. All right, Zach S.
F equals ma.
There we go. That right there. This right here is Newton's second law. I was starting to feel a little nervous we weren't going to get that one. But that equation right there is what we're using for this chapter. That is the primary equation of this chapter. And it's, like I said, we're going to be studying this one a little more in depth next time. It's a pretty simple equation. I'm not going to be stressing you out with the math because there's only two things. You multiply them together, you're done. But that right there describes the whole law. All right, Sergio.
I have bigger.
Oh, you unmuted, or sorry, you muted rather.
I lost my pages. I think what I had was a bigger force or time implies a bigger impulse.
A bigger force or a bigger time gives a bigger impulse. And I have a little bit more I'm going to say on impulse, but I want to see first what Zach E has to say, because he might cover it for me. Zach E, what is your thing to share?
I was gonna say that the kicker is in contact with the ball for like 0.008 of a second, and in that time he applies almost a ton of force to the ball.
So it was something like, you said 0.008, right?
Yeah.
Now, with that, here's what I'm going to add about impulse. And like I said, impulse is actually something we're not going to study in depth this chapter, but it's going to be a big unit down the road, not too far down the road. Impulse, remember, was force times time. And what Zach E said goes right into this. If you have, if we assume a certain change in speed, then we can assume a certain impulse. Is needed. And one of my favorite things about this video is they use this idea of, they say you can have a really big force times a really little time, or you can have a really little force, and they make this visual representation for us that just by definition, when you have two things multiplied by each other, and those two things say are going to equal 25, just to throw a number out there, if you make the first thing big, the second thing has to be small. If you make the second thing big, the first thing has to be small. By definition, if I'm going to get that number 25, that has to be true. Now, one reason I'm bringing that up is the same thing. I know I scrolled past it, but this is going to be the same thing here for F equals ma. If we're requiring a certain force, we might want to either increase the mass or we increase the acceleration if we're looking for a certain force. This is something called direct variation. Direct variation just says that you're multiplying your objects together, as opposed to inverse or indirect variation, where one thing is being divided by the other. One reason to bring this up is this is how the equations were created in the first place. they look to see, if you make something bigger, what does that do to the equation? Versus if you make something bigger here, what does that do to the equation? Or what does that do to the quantity I'm looking for? And so therefore our equations were born out of this idea of, if I'm looking for a certain y value, how do I adjust my, what do I do? What happens when I adjust one or the other of my other variables? Not something I'm going to focus on in depth right now, but it will be something I bring up a couple times this year as we teach you how, not just what the equations are, but how they were made in the first place. Any questions? Okay, Philip, if it gets bad enough, you got to go, just go. Let's go ahead though, and let's go back to our last video. And then we'll do the same thing. And then, like I said, we're going to take a short little group quiz together to see if we understood what it was talking about.
Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier.
The object of making the tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push against the body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important to have some speed and momentum as you're going in to make that tackle. The better if you're able to use that to your advantage, the better you're able to make contact and get a guy down right away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's Cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls in a Newton's Cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released, mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is, the energy of motion of two runners. After they collide, that energy is dissipated and deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pad. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take him back. At the point of contact, hopefully that's where the ball stops play in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, We have Newton's third law to thank.
P equals MV.
P equals mv. And did you catch what P, M, and V represent?
Well, I know momentum and velocity, but I forgot what the P is.
Actually, you're super close. M's actually going to equal what it equaled for us before. It's going to be your mass. Although we haven't used mass entirely yet. M will be mass. V will be velocity. And since M's already been taken, M's already been claimed by other things, they actually, my guess is they just went for a letter nearby to describe momentum. And momentum is so big that it's another one that we're going to approach as its own big topic not too far down the line. We won't be talking too much about it right now, but once we talk about momentum, we're definitely going to be coming back and talking about Newton's third law plenty. All right, Tanner, you're next.
Newton's cradle.
Yeah, what's the Newton's cradle?
It's like this ball thing. There's a stand. There's like, I think 4 or 5 balls that hang on strings. So you pull one back, let it go. It'll transfer the force of energy through all the other balls and then the last one, and then keep swinging.
Perfect. And I'm just going to make that. You've probably played with one before. I have one that I normally have in my classroom. One of my physics students last year, I was gone for a sick day or sub day or something, and I came back and one of the strings was broken. Still got to figure out how to fix that and if I can fix it. But Newton's cradle, I'll also call it the click clacks, just because that's the noise it makes. But the whole idea is it is a great way to visualize any change in momentum or this idea of Newton's third law, which we haven't actually gotten to yet entirely. Okay. Gage, you're next on my screen.
So when a player when is running, whether it's with the football or not with the football, or if they're tackling, the equation for them, getting tackled is P equals MV, right?
All right, so that's the equation that Cade gave me right up there.
Yeah.
But I'll add the equation of a tackle is the momentum equation. All right, Philip. You're muted.
Thank you.
There we go.
Every force has an equal opposite force pushing against it.
Every force has an equal but opposite force pushing against it. And let me say that right there is Newton's third law. And let's take, for example, have any of you ever played volleyball in your life? When you play volleyball, this is just a really good example because it's you exerting a force on something. Now, let's say it's coming in and you're going to go for a spike. Obviously, you put a force on the ball, right? The ball moves. You go to spike it and it's going to move. Does your hand ever hurt afterwards? Why?
because the ball's smacking you right in the hand, or if you're dumb like me and miss, it'll hit you in the forearms.
Yeah, no, I hear you there. All right. But I like the way you phrase that. The ball smacks you in the hand. In that process of you smacking the ball is also smacking you. And even though it's the force of you on the ball you see, it's the one that's a little more clear because you watch that ball then move. You're not entirely moving. You feel that force yourself. And I know, like, whenever I walk out of a volleyball game, like, my arms would be all red because it's evidence of the force of the ball on me. And what Newton's first law is saying is not only does it exert a force, but whatever force it exerts has to actually be the same as the force I exert on it. So that doesn't mean that they cancel each other out, certainly, because, like, obviously the ball keeps moving. I do not. How that force is seen is different. But it is true, anytime you exert a force on anything, if you kind of push your brother actually, there is a resistance force of him pushing back on you, even if it's not with his arms. Does that make sense? If we were in the classroom, what I usually do is I'll stick somebody in my office chair and I'll wheel you around the classroom. And as we push, we can see the force of me on the person in the chair. But what's less evident, unless you're the one experiencing it, is the force of the person on the chair on me. Okay, so it's not that I've just to kind of bring that one up because that one's sometimes been the one that's the hardest for people to get their heads around. A lot of people try to think that that means they cancel each other out. I'm going to add equal but opposite forces in this case, because they're on different objects, do not mean the forces cancel each other. Let's say it this way. Two forces can only cancel one another when they are acting on the same object. So in other words, you push on your brother and somebody else is pushing on your brother in the other direction. Both actions would be on your brother. And I didn't mind bringing that one up because I know the video doesn't explain that. One, two, three, four. Okay. Zach S., you're next on my list.
Elastic collision is a collision with no loss of kinetic energy.
Perfect. The Newton's Cradle is a good example of that. So, elastic collisions, and then there's also going to be something that's called inelastic collisions you may or may not bring up. Those, again, are going to be important enough. Well, after we do our unit on car safety features, that will be the next thing we talk about, the very, very next thing. And for that, we'll talk especially about roller coasters, in case you like those at all. Okay, almost done. Zach E., you are next.
Elastic and non-elastic collisions.
What about them?
How like non-elastic, it's like it doesn't deform, like there's not energy lost and like deforming the object or heat or whatever. But elastic collisions is like in football players, it's the energy is diffused through like compression of the player.
Perfect. I think you used the word non-elastic, but you might have said inelastic. I wrote down non-elastic for some reason. All right, so inelastic collisions still do not lose energy, but the energy is taken from the kinetic energy and becomes other forms of energy. Like heat, they give as an example. Sound, they give as an example. And I know I'm going kind of fast. I'm trying to be kind to Philip here. But we'll pause for a second because I know I did go pretty fast for you guys to copy that down. And then go ahead until you finish writing, but Emily, you are next.
Do you want me to go now?
Uh-huh.
Okay. I just got that I may have missed it, but the total motion must be the same before and after the tackle, and then that like equation is like P before equals P after.
All right, so your momentum, I'm going to say stays constant. Or rather, more appropriately, the change in momentum. In other words, delta P before equals delta P after. That right there is its own law. It's called conservation of momentum. We'll be spending a whole unit just on that. And then to bring it back to your cars, it helps describe a lot of your car features. In fact, in the last video, in the second law video, they bring up the idea that impulse is the change in momentum. So we're going to talk about how that idea of impulse actually will fit in right with this change in momentum idea. All right, Sergio.
I have nothing, but let me think of something real quick.
Okay.
Well, like I guess with like, if we think about it, if we're using like the terms of like the football, like video, the footballer who has the football, when he runs into another football player, all that like, you know, energy goes into the other football player, you know?
So, and this goes with Newton's cradle again, but I think we don't usually think about it in terms of players. The energy from one player can transfer to another player when they hit. And only when they hit, they have to come into contact. You can't just be like, I give you my energy. That doesn't work that way. But when they hit each other, you can see that. Like somebody goes in for a tackle. The first guy's coming in with all this energy. And the second one usually then feels the effect. Kind of like my arms with the volleyball. as that energy is being transferred over. And I like too, the one guy they interviewed said that your whole idea is if you want to push them up when you go in for the tackle, not necessarily down. He talked about you want to push them up because you actually are more effective in stopping them. Because then they have to fight both you and gravity. Where if you're pushing down, they actually can use gravity to their advantage. But if you separate them from the ground a little bit, they don't have that same friction. All right. I want you to finish copying down. Once you finish copying your stuff down, I want you to have a staring contest with somebody on the screen. Then we're going to take a short quiz to see how well we absorbed these things. And then that'll be it. So just when you finish writing, find somebody on the screen to have a staring contest with.
Do we have a final in this class?
No, very good question. If you did, I definitely would have brought it up by now. I always tell you about your tests at least a week in advance. I am going to do everything by when we finish a unit, finish a topic, instead of by where we are in this term.
Oh, okay, cool.
Yeah, so you took one after motion. You'll take one after we finish forces, but we're just still only at the beginning of forces. This is just our second week on them, so it'll be a little while.
All right, cool.
Yeah, very good question. All right, Zach E., are you still writing?
No, I just finished.
Okay. I was going to say, I thought maybe you were looking up earlier, but I couldn't tell. Okay, so now you guys are you probably used Nearpod a crazy number of times. Believe it or not, this is only like my first or second time ever using Nearpod. So go to joinnearpod.com and type in the code XZLA8. And you give me feedback about anything you see or hear, because like I said, I'm still not too familiar. I ran through this yesterday, but I've never done it with the class. All right, I see Gage is in. And Cade. And again, this won't be for points. This is just, we're testing ourselves to see how well we understood what we just talked about. Philip's in. Tanner and Emily are in. Go ahead and run through the quiz, and then I am going to go through the answers with you. Zach E. and Sergio are in. I think just one more of you to go. 8. I think everybody's in. All right. All right, when you finish, just hang tight so we can go over the answers.
Miss Zacharias.
Mhm.
I'm gonna go fill up my water bottle.
Okay, go ahead. We're almost done. Meaning most of you, you're almost done answering the questions. Okay, first of all, as we look at our preconceptions about these objects, here's how we did. I took your names out, but everything that's in red was an incorrect answer. Everything in green was a correct answer. And what I see is as we go further down the line, I'm seeing a lot more green on this half, but on this half, still plenty of red, which honestly, normally I do see, because it just tells us there's still some things that you guys believe about some of these subjects that we're going to be tackling this chapter. So I want to go through the answers to this with you very quickly and then get you out of here. So first of all, a force is required to keep an object moving. Most of you said that that was true, but that is false. And the word there is keep, means the object was already moving. So a force already was applied. You do not need a force to keep it moving. Kind of like that idea of, we do believe usually, like you roll a ball, you see it stop, you think, oh, no force applied, but really friction did apply there. All right, Cade, would you read this one?
An upward moving object must be experiencing, or at least usually does experience, an upward force.
So if it is moving up, does that mean it's got a force pushing it up? In the moment, it doesn't. Do you remember when we did the two-stage rocket?
Am I answering?
All of you.
Okay.
Which you're included in. Do you remember doing the two-stage rocket experiment here in class where we watched the animation? You had something pushing it up, and then you had another booster pushing it up more. But then that one flamed out and it still was moving upward. And then it fell back to the earth. It does not need to have a constant upward force to keep it going up. It does mean something pushed it up initially, but the B experiencing means in the moment. Okay. Philip, would you read this one?
A rightward moving object must be experiencing, or at least usually does experience, a rightward force.
All right, let's have everybody respond with their thumbs, because right now a lot of people are kind of doing their own thing. Thumbs up for true, thumbs down for false.
Let's go.
I need Kate's thumb still. Kate, make sure I can see your thumb. Thumbs up for true, thumbs down for false. All right, most of you saying false. That is correct. Same reason as for the upward. Maybe it had something get it started, but not in the moment. All right, Tanner, go ahead and take this one. Read this one for us.
Ball is moving upwards and rightwards towards its peak. The ball experiences a force that is directed upwards and rightwards. True or false?
Show me with your thumbs. Thumbs up, thumbs down. Kate, thumb sideways doesn't mean anything. Okay. Kate, you with us? You seem distracted. Okay. And Zach S, I can't actually see your thumb. And Zach E, I actually can't see your thumb either. All right, a little more split on this one. This one is also false. Again, the force maybe got us started, but it does not need to continue experiencing it to keep moving that way. Once it's moving that way, it wants to move that way in a straight line at a constant speed forever and always until another force acts on it. All right, Gage, would you read this one?
Yeah. If a person throws a ball with his hand, then the force of the hand upon the ball is experienced by the ball for at least a little while after the ball leaves the hand.
All right. Show me your thumbs. Only 2 people got this one right. And who knows, it might be some of the same people because only 3 of you are telling me the correct answer. Now this one's worth writing down. A force only applies while it's in contact with the object. Once there is no contact, there cannot be a force, unless you're talking about gravity and some of those other forces, which we're not talking about yet. But the forces in terms of what we're talking about now, which, by the way, we haven't actually defined force yet. A force is a push or a pull. That's all it is. You need to have contact with the object to be able to apply the force. Tanner, you still alive? No? You did have a big weekend. All right. Zach E, would you read this one?
It's like eating a bagel.
Sorry to catch you.
A
cannonball is shot from a cannon at a very high speed. The force of the explosion will be experienced by the cannonball for several seconds, or at least a little while.
Thumbs up, thumbs down. And Zachy, I can't see your thumb. All right, most of you flip-flop, because most of you originally had said that this one was true before. In fact, only one person said it was false. This is false for the same reason. I left it on the screen for a purpose. Once they're no longer in contact with each other, the force doesn't apply anymore. All right. Zach S., would you read this one?
If an object is at rest, then there are no forces acting upon the object.
Thumbs up, thumbs down. Zachy's back and forth. There we go. Emily, did I see a thumb from you? Okay. All right, most of you stuck with your original answer. Unfortunately, most of you were wrong last time. And let me draw out for you a very simple reason why, and this is the sort of thing we're going to start focusing on next class. I have a box. Amazon Prime Day was last week. You got a box left over from it. It's sitting on a table. It's not moving, but are there any forces acting on it? There's one you definitely should think of. What's one force that absolutely is acting on that box?
Gravity.
The force of gravity is pulling it down. Now, it does have a force of the table pushing it back up. That's going to be something we're going to start talking about a little more next time. These two forces are on the same object. They're going to be the same strength. They are going to cancel each other. But there most definitely are forces acting on the box. Gravity doesn't stop existing, for example, just because something's not moving. All right, home stretch. Sergio, would you read this one?
Objects do not weigh anything when placed in a vacuum.
Show me your thumbs. Emily, you can't give me a side thumb. Okay. This one.
I don't know why I put thumbs up because I put 5.
On this one, we actually had most of you get this one right on the
yeah,
first
like I accidentally did this, so I don't know why.
This one is going to be false. Not having air around you doesn't get rid of gravity, in other words. I think this one's really important because we're going to watch the movie Apollo 13 later this year. And I always ask my class, how do you think they filmed this? And when I started my career, most of my students told me that the actors filmed in a vacuum. What are the two problems with filming in a vacuum?
There's no oxygen.
No oxygen, no air. So the actors would not be able to film a complete movie in those conditions, let alone a scene. And second of all, vacuums don't get rid of gravity. Gravity's still going to exist whether you have air around you or not. For example, we saw with the hammer and the feather video a couple weeks ago, they still fell, even when we took all the air out. All right. Philip, would you read this one?
And all objects weigh the same amount when placed in a vacuum, regardless of their mass.
Show me your thumbs. So what this one is saying, let me clarify this, is the feather and the hammer weigh the same amount as each other when we take all of the air out of the room. Would an elephant and a feather weigh the same amount when we take the air out of the room? That one is false. Whatever they weigh with air, they'll weigh without air too. All right. Kate, let's have you read this one.
An object weighs less on the moon than it does on the Earth.
Show me your thumbs. That one is true. And if you notice, this is problem number 10. The first 9 were all false. This is the first one we've come across that is true. They do weigh less when we go to another planet or to the moon. On your mark, get set, go. Let's see. Zaki, would you read this one?
The mass of an object on the moon is the same as the mass on Earth.
Show me your thumbs. Emily, did I see your thumb? All right. Good job, guys. Your mass does stay constant when you move between interplanetary systems. Weight, of course, though, does not. All right. Sergio, would you read this one?
A high-speed object, say moving at 200 miles per hour, will weigh less than the same object at rest.
Now this one's starting to get kind of freaky. What do you think? Yep, Emily, that's okay. Cade, what do I have from you and from Tanner? All right. If you said false, you are correct. Moving fast does not change the weight unless you're moving close to the speed of light, but that's way faster than 200 miles per hour. Way, way faster. And it actually will make your object heavier, not lighter. But moving at a regular pace that we could actually achieve on Earth, not going to make you weigh any different. All right. Zach S., would you read this one?
A high speed object, say moving at 200 miles per hour, will possess measurably more mass than the same object when at rest.
Does your mass change when you move fast? Show me with your thumbs. Sergio's kind of giving me I'm not sure about this one, All right, Zachy, just waiting on your thumb, and Cade waiting on your thumb. Okay. Sometimes you do it just for a moment, but I'm looking at somebody else's face, so I miss it. All right, that one is false. Although, at the end of the year, again, turns out when you're going really, really, really fast, like way faster than 200 miles per hour, it actually does change your mass. You actually get more mass, but you have to go way faster than this, like faster than any human could ever achieve. All right, 2 more to go. Well, 3 more to go. Philip, would you read this one?
Weight is measured in pounds, mass is measured in newtons.
All right, we haven't even talked about this one yet. Just go ahead and make an educated guess. Thumbs up, thumbs down. I'm getting kind of close to 50-50. And again, we haven't covered it yet. This one is false. Weight is measured in pounds. Weight is also measured in newtons. For mass, we're going to use kilograms. I'm not going to focus on that right now, but we will next class. All right. Tanner, would you read this one?
A free-falling object still has weight.
Show me with your thumbs. Good job, guys. That one is true. Even if you're not touching the ground, you still have weight. And last problem. Sergio, would you read this one?
Weight is the result of air pressure exerted upon an object.
Show me with your thumbs. And keep those thumbs up because I had to turn away. All right. Missing one thumb. There we go. Good job. If that was true, your weight would change in a vacuum.